Hi, I'm Carly McAvoy, and this is homework 8B. We're talking about similar to what we did last time, only now we're using T instead of Z. So I'm going to be flipping back and forth between the computer a little bit to show you some things that are going to be important to you. But we're going to start off answering this one right here. In statistics, what does DF denote? Remember, that's degrees of freedom. So the degrees of freedom is what you want to say and not distribution of freedom. And then the degrees of freedom for this sample, well, the simple sample has 22 and degrees of freedom is one less than that. So we would say B denotes that. The second one says use technology to find the p-value for a right-tail test with n equals 17 and test statistic 2.793. I'm going to show you how you could use the table, and then I'm going to show you, going back over there, how to do this with technology that I've got a link in your homework for, so you don't have to go find that on your own. If you have a TI-84, TI Inspire, you can do it on your calculator. Google it. It's great. You can just use that. But our TX 36X Pro, which only costs us $20, doesn't do that. Okay. So, oh, maybe I took them out. No, here we go. Degrees of freedom, yeah. So the thing we had said that there was n equals 17, so we have 16 degrees of freedom. And then it says the test statistic is 2.793. So if you look across here, we would look for 2.793. Do you see that 2.793 is between these two values? That's why the table falls short, because I know it's some number between 2.921 and 2.583, but I don't know which number. I know that my number falls in between there, 2.791. Let's say that they asked us for 2.921, then we would just go right up here and say, well, it was a one-tailed test because it was just a right-tailed test, and so in the one-tailed test, if it was really exactly that number, it'd be 0.005. But for our purposes, we know it falls in there. So if we go up, we'd say, I don't know. All I know is my p-value falls between these two numbers. I don't know exactly what it is. And so that's not really cool. I mean, I know exactly what it is because I can see here it's 0.0065, but how would I know that, you know? So anyway, I need to use technology. The t-table doesn't help me when it gets to be this obscure. So let's go check that out. Hopefully I have, we'll go to homework and tests. Yes, wait a second. Stay on there and save all those changes. Oh my gosh, if I just lost all those changes, I'd be losing it. There's only 12 questions on here. They take a little bit of time. Okay, let's go back up here to 8B. First question we just did, degrees of freedom. 1 minus whatever you started with. I'm not going to worry about that one again. Look at, you hit number 2 and you see how this instructor tip comes up. After you've done that once, it doesn't come up again. So if you came back later and opened it, it would just say over here, it would still say view instructor tip, but it doesn't pop up for you after the first time. So here it says use this link for a free online calculator. So I'm going to take that. There's other ones you can find. I actually have used other ones in the past. This one seemed fine. To me, they're all kind of the same. Okay, so what you're going to do then is go copy that link and paste it into your URL. And here's what comes up. And then we want to find a p-value from t. Okay, so they say, what is the t-value that you have? And we were given 2.793. And then it asks you for the degrees of freedom. Now, other ones, our n was 17, so our degrees of freedom was 16. Other things will ask you, is it a one-tailed test or a two-tailed test? This one just always assumes it was a two-tailed test. So when I compute that, it's telling you, okay, the two-tailed p-value is 0.0130. Let me write that down, then we'll flip over, is 0.0130. So, well, that's too bad because that's not what I had, right? I had just a right-tailed or one-tailed test. So what would I do? Well, I would just divide that by 2, and that would give me the one-tail, right? And the one-tail value then is 0.0065, half of that. 0.0130 divided by 2 is 0.0065, which is what our value is. So you want to check, and it's always going to give you the two-tail. So if you have a two-tail, you're in like Flynn, and if you don't, then you just say, okay, I'll just divide by 2 and I'll get that. So I put that link up there, but feel free to go find a different link if you want to. So for number 3, they say use the table of values. And all they're asking you to do is say, well, my p-value is in this range, right? That's what I was showing you could do with the t-table, is just say, I don't know exactly what it is, but it's just in that range. Well, let's take a look at what we have. We have n equals 13, so our degrees of freedom is 12. And then we have this 3, doesn't matter if it's negative or positive. Left tail test, so it's one tail. Okay, so 3.053 for 12 degrees of freedom. 3.053 is in between these two values, and it's 1. It's somewhere 3.053 is a little bit less than this, but it's more than that. So if we go up to the one tail test, then our answer is between 0.005 and 0.01. So we could choose it that way. If you don't like that, what I find is that people just really don't, I don't think I need this anymore. They really don't like that. Doesn't make sense to them. They don't like it. But I just showed you that it's this. But we can just go back and use technology, and then you could easily give the answer that way. So if you want to, for number 3, I've got that same tip posted. So we're going to use that same thing. I can go back to that, and we can just do this one since it's up here. We have n equals 12, so our degrees of freedom is 11, and our t-value is negative 2.268. So let's go see what that is. Negative 2.268. Degrees of freedom were 11. And we can compute. Again, it's giving us a two-tailed test, 0.0445. And I only have a left-tailed test, so I would want to divide that into 2. And when I do divide that into 2, I get 0.02225. So then you can say, okay, where does 0.0225 fall in here? Which between one of these two values does it fall? Okay. 0.022. 0.022 is a little bit less than that. 0.022 is a little less than that, but it's a little more than that. Looks like that to me. That wasn't all that much easier either, but you find a value to say what it's in there, or you can just use the chart like we did. Okay, so I put that instructor tip on all of them, but I think if you go back, later on, if you go back, it doesn't jump up the second time. It just still has it up here if you want it. But if those are annoying you, just close them. Doesn't matter. Okay, so use your table, or go and actually find an exact value. That's up to you. All right, so again, we're supposed to use the table for this. The n equals 15, so our degrees of freedom are 14. That's right here. Test statistic is 1.954, so we come over here and find 1.954. And 1.954 would be in between these two values, between 2.1 and 1.7. So then it's a two-tailed test. So I go up here to the area in two tails, and then my range is between 0.05 and 0.10. So 0.05 and 0.10, or B, is my p-value range. And again, you could go find that on technology and then decide which range it fits into, whichever of those makes the most sense to you. All right. 4, 5, 6, and that was 8.4.7. B, we just answered that. Let's take a look at 8. No, page 8, number 5. Okay. Yep. Oh, they have a display here that we need to see. Holy kaliki. A lot of stuff. Okay, let's get it out. Okay, let's start from the beginning. Assume that a simple random sample has been selected. Hey, you know what? We always want a simple random sample. Sometimes they just say assume an SRS, simple random sample. That's so important. You cannot overcome bad sampling with good math. Not possible. If you have a bad sample from the beginning, so on all these you want to assume a simple random sample. Has been selected from a normally distributed population and test the given claim. Identify the null and alternative hypothesis, test statistic, p-value, critical values, and state the final conclusion that address the original claim. In a manual on how to have a number one song, it is stated that a song must be no longer than 210 seconds. A simple random sample of 40 current hit songs results in a mean length of 240.9. Notice that in the last chapter, we were using proportions, and now all of a sudden we're using mu or means. So it's the same type of idea, but remember the formulas are a little different. We'll go look that up in a second. Okay, in a mean length of 240.9 seconds and a standard deviation of 57.02 seconds. Use 0.05, that's pretty common, and the accompanying mini-tab display to test the claim that the sample is from a population of songs with a mean greater than 210 seconds. So we think that the mean is greater than 210. It's stated that a song must be no longer than 210. So in my mind, what they're saying is it could be that it's no longer than. It could be less than or equal to is what they're saying. It can't be any longer than, but it could be less than that, or it could be exactly equal to that. So they're kind of saying that so that when we go to write the alternative hypothesis, then we want to talk about that, okay? Because they've already gotten, basically we're using equal, but what we should really be using is less than equal, because that's what they actually stated. So since we've already used the less than and equal to part in our claim, we use the opposite, or the other part that's left, which is the greater than. And so I think it would be D. The mu is exactly 210, and the alternative is that. If we wrote the mu with as stated, you would see that while mu, the null, we're thinking is less than or equal to, therefore the second one would have to be O, but the alternative that it could be greater than. You see how we've used all three parts, less than, equal to, and greater than? That's a little confusing for students. So identify the test statistic. So we want to find the test statistic with a t-value. Remember, you have a lot of resources available to you in Math Excel. So if you don't have your notes nearby or whatever, go to view an example and get that formula. It's going to give you those formulas in there, which is really sweet. Oh, wait a second. They gave us a mini tab display here, so I don't probably need that yet. Oh yeah, they did. Well, I forgot about that. In this particular problem, we could go find that, but they're going to tell you, read the mini tab display, because that's what we're doing. So anyway, this was number 5. We're not even up to speed, so yeah. Okay, let's go back and look at the paper. I've got it up now, the mini tab display. Mini tab is a statistical calculator that we don't have access to, but this is what it would look like. So they say, identify the test statistic. Well, that's T. We're using this because we have the sample standard deviation, but we don't have a population standard deviation, and we have we have to use it then. 40 is a relatively small sample too. So T is 3.43. We didn't have to go figure that out because it was given to us. Okay, then what's the next part? The p-value is, well, that's another thing they gave us, 0.001 is the p-value. Next part they're asking, identify the critical values. Well, the critical values are a little different. When you're talking about the t-values, we need to use a table. Did they put that in there? Yeah, they do. Man, we got everything in here. So we're going to go to our chart knowing that we have the area in the right one tail, just to the right, and where our degrees of freedom is, how many? It was 39, right? So let's take a look at this. Well, remember, oh, they do have a 39 in here. I was going to say they don't always have the exact number you want here, but they do. So we go to 39. Up above, we know we have area in one tail, so we're looking up here, and the area in one tail, what was it? Mini tail, I can't see it. We're talking about 95%. So we have 0.05, right? 0.05, 95%, that's what that is. So we go to 0.05, 95, okay. Why did I choose 0.05? Because it has in the mini tab display that it's 95%. And so if it's 95% and it's all in one tail, what we have left is that 0.05 that's left over there. So I go to that, I go to 39, and I follow it over, and I get 1.685. We did critical values a few lectures ago, and if you're not remembering that, you may want to go back and look at it again. Or maybe I can show you here what we're talking about. If we have 95% confidence that we're using, sort of, remember this is 50% over here. We are up to 95% here. And what's left over here is the remainder, 0.05. So we have this little tail that's 0.05. Was that left or right, actually? Yeah, it was right. So that's what we're looking for, is what's this value of t right here, this critical value. And what does the critical value do? The critical value separates the usual from the unusual, right? So that critical value is that cutoff point. So we got that using the table, and that was 1.685. I'm just writing it down, but you can't see it. But okay, so state the final conclusion that addresses the original claim. Well, we still are using our p-value, and we're comparing it with our significance level. And that's less than. So when it's low, what does that mean? When it's low, the null must go. So we reject the null hypothesis. So forget about fail to reject. Those don't either one interest me. Reject it. There is sufficient evidence to support the claim. So if you're having trouble picturing what that means, once you say reject, be a little sad about that, and that means you're going to be happy about the other one, right? So there is sufficient evidence to support the claim that the sample is from a population of songs with a mean length greater than 210. There is insufficient evidence. No, we like this one. Okay, and then what's the last part of this question? 5. Seems like there should be another part. 8, 9. Oh, here it is, right here. What do the results suggest about the advice given in the manual? Well, it suggests this. We just found that we said that the null hypothesis should be that basically the song should be less than or equal to, and we just rejected that. So we don't believe that songs need to be 210 seconds or less. So therefore, I don't think they did. The results suggest the advice of writing a song that must be no longer than 210 seconds is not sound. We just had a sample of hits, 40 hits that were all longer than that on average. So we don't believe that their claim, we don't believe that the advice is very good based on our math. Did we pick 5 anomalies? Well, that's the idea, is that if we did pick, if their advice was sound, there's a 0.001 chance that we would get the results we got. So we can be pretty confident, like, hey, that's really small. So I don't think that's going to happen by chance if their advice was right. It's very unlikely to happen if they gave us good advice. Okay. A simple random sample of 50 adults. Okay, they gave us the information here again to go over. That's good. A simple random sample of 50 adults is obtained from a normally distributed population. Sorry. Each person's red blood cell count is measured. The simple mean is 5.25, and the sample mean, I say simple, 5.25, and the standard deviation is 0.52. Notice we don't have a population standard deviation, so we're talking about a t-test. Use a 0.05 significance level and the given calculator displayed to test the claim that the sample is from a population with the mean less than 5.4. So their claim is that it's less than 5.4. And our claim, then, our null hypothesis is going to be that it's equal to. Okay, so when they start to say stuff that's at least or more, less than, equal to, it gets more complicated. If they just say less than, or if they just say greater than, they've stated the null hypothesis for us, and all we have to do is write it down as they stated it. It gets more complicated when they say it a different way. The test statistic is the t-value rounded to 3 places. That's this, negative 2.040. Rounding decimals, one of the downfalls for people in statistics. You want to make sure you can do that. Okay. Secondly, identify the p-value. P-value is given right below that to 4 places, 0.0234. Identify the critical values. Okay, that's a little different, right? We're talking about a less than. When we're talking about a less than, our critical value is going to be negative. Remember, our table only has positives in it. I apologize again if you cannot read this. I can read it when it's on the screen, but if not, you're going to want to get your own copy to look at. I don't remember how many people were in the sample. 50 people. Notice we go from 45 to 50. There's no 49. We'll just use 50. It's close enough. This was a left-tailed test. Yes, a left-tailed test. We're using the 0.05 significance level. So we can use the, this is Warian one tail. 1.67, we're going to use 0.5 in one tail. Yep, because we can, just because they gave us this already, we can just do that, use that 0.05 as we're doing this. So we're going to 50, and we're going over here to where it says 0.015, and we go, oh, holy crips, I didn't show that. Where's my fingers? There we go. We're going down to 50. The area is in one tail because we said it was just a left tail test. And the area in one tail for 0.05, since we're using 0.05 significance. And then we just go down here, 50, and I get 1.676. But remember, this only gives us our positive values. Since we're talking about a left value, it's got to be the negative, right? If you think about it this way, we're talking about, we think it's less than. So when it's less than, we're going to go, there's some critical point over here where it's usual and not usual, right? So we're interested in this point, critical point that separates those, right? Okay, so be careful with the sign thing. State the final conclusion. The p-value is less than the significance level. Therefore, if it's low, then the null must go. So we are going to reject the null. So forget about these two fail to rejects. And if I reject the null, sad for the null, happy for the alternative. And so there is, because our choice then is there is sufficient evidence or there is not. Since we rejected the null, there is sufficient evidence then to support the other claim, which is then D. And then there's another question. Where is it? Here it is. There is enough evidence to conclude that the sample is from a population with the mean less than 5.4, so it is unlikely that the population has counts that are too high. Wowza. Let's go back and, I need to reread that. I'm hopefully that I'm not the only one. Our claim, the sample is from a population with a mean that's less than 5.4. And we do think that that's true. We said yes to that. So we think that there is evidence to support the claim that the sample is from a population with a mean less than 5.4, which means there is evidence to conclude the sample is from a population with a mean less than 5.4. That's true. So these one of us said there's not evidence. We just saw there was evidence to support that. We just saw that, yeah, it looks like it was, we had the happy face next to that and we supported it. So there is evidence to conclude that. So it's possible the population have counts, the population have counts that are too high. It's unlikely, it's unlikely. We got this really small probability, so it's unlikely that those are too high. Okay. The wording, well, just warning you, be careful with the wording. 6, 7. Okay. Assume, now we don't have, suddenly, we don't have something to look at the mini-tab reports or whatever. We have to do this stuff on our own. Assume that a simple random sample has been selected and test the given claim. Use the p-value method for testing the hypothesis. Identify the null and alternative hypothesis, the test statistic, the p-value, and then state the original claim. That's always what we're doing. The ages of actresses when they won an acting award is summarized by the statistic n equals 84, mean is 35.8, and the sample standard deviation is 11.6 years. Use a 0.05 significance level to test the claim that the mean age of actresses when they win an acting award is 34 years. We think that the mean age is 34, so we're going to look at if they say it is, then we're looking at it could be less than or it could be more than. So we want the does not equal version, which is right here. Okay. Null hypothesis, mu, alternative hypothesis. Identify the test statistic. That's not the critical value. That's a test statistic. The critical value is the one we go to look at the table for. So let's go over here and look at number 7 and get that formula if needed. There's the instructor tip, and we're going to go to view an example. They're going to help us find that significance level is 0.01. The there it is. It's coming. It was coming. The t is x bar minus mu and s over the square root of n. We have all those values given to us, so we should be able to go back and find that. So x bar they gave us is 35.8, and mu, well, that's what we were talking about, is 34. And then the standard deviation, s, was given to us, and n was 84. So you need to know when to use what formula to find those test statistics. Okay, so 35.8 minus 34 divided by this fraction, which is 11.6 over second function square root of 84. Look how beautifully that is. So easy to enter. It's so quick to find it. And so we get 1.422 to 3 decimal places. That's a pretty typical or normal test statistic. That means that if I was looking at this where I have 0 in the middle and here's 1 and here's 2, I'm just like right here. Doesn't look that unusual. This is a two-tailed test too. So I'm looking at it over here, and I'm also looking at it over here, right? I have two critical values because it's a two-tailed test. Two-tailed test because it's not equal to. So let's go find that p-value on the computer, but we could find it without that, but what the heck? Because it's not going to be an exact number unless we have the computer to do that, and I will try to make sure we have that up for you when we do it. So let's take a look at this one. Stop. Let's view that instructor tip again. I probably left it up, actually I did. Okay, so we're going to go over here, and our t value that we just found was 1.422. And this was 84 people, so our degrees of freedom is 83. We have a two-tailed test, and they're going to give us a two-tailed answer, so we're all good on that. And when I find that, I get the two-tailed test equals 0.1588. Okay, in the class that I just taught on statistics, that's not the one I want. When I was teaching this, I would get people who would do a calculation for the p-value, and they would get like 4.3. Why can that not be possible? Because the entire area under this curve equals 1. That's the most you could ever get. It's 100%. Okay, that'd be 1. But anything else is some fraction of 1 or part of 1, like 0.1588. That makes sense. 15.88 would not make sense. Your decimal's off by a couple of points. That should be a red flag. You can't have more than 1 for a p-value because it's a part of that area under the curve, which only can be 1 altogether. Okay. State the final conclusion that addresses the original claim. This is greater than the significance level of 0.05. Therefore, if it's high, the null will fly. When it flies, it means fail to reject. Fly, fail, okay, FF. So forget those two. And if we fail to reject, then we're happy with that one. And that means we're going to be sad with the other one, which means there is insufficient evidence to support that, right? That's an easy way, to me, to my head, to think about that. That was 8.4.11. Okay, let's go on to, this was 14, 13. Okay. Oh, that's all messed up. Okay, assume that we have tables built in this one. We do. These ones that have the tables built in, they go on and on forever. They want you to use that. But, okay. Assume that a simple random sample has been selected and find all that stuff. A simple random sample of 25 filtered 100 millimeter cigarettes is obtained, and the tar content of each cigarette is measured. The sample has a mean of 19.2 milligrams, a standard deviation of 3.41 milligrams, and use 0.05 significance level to test the claim that the mean tar content of filtered cigarettes is less than 21.1. How nice when they say it that way, because they straight out said less than. That's our alternative hypothesis. So we know the alternative hypothesis needs to be less than 21.1, but our null hypothesis is always equal. So forget that one. Here we go, B. I love it. When it's stated that way, it's the easiest kind. If it's just less than or just greater than, it makes it easy. Identify the test statistic. Remember that formula that we just used? It's already gone out of my head. Not really. You're going to do x bar minus, yeah. So it is x bar minus mu over s over the square root of n. So the mean, sample mean is 19.2. That's what x bar means. And the mu is the 21.1. Notice we're going to have a negative test statistic, but we have a smaller number minus a larger number. And then S, standard deviation, is 3.41 over the square root of the n, and a random sample of 25. So we have 25 there. And then I can just go at it here. So 19.2 minus 21.1 divided by this fraction that is 3.41 over square root of 25. Can we just say 5 there? I think we all get that. And that gives me negative 2. I didn't have that. 2.786 to 3 places. Okay, well, that's kind of rare, right? Because if I'm looking at that here, we're talking about a left-tailed test. That's why it makes sense that our test stick was negative. Here's 1, here's 2, and over here we have negative 2.786, and our p-value is the area to the left of that, which is a relatively small part of our function. I can go find that using that little program that I had. Let's do it. We had negative 2.786, and we had 24 degrees of freedom. Our n was 25, so we can compute that, and it's a two-tailed test, but ours was only a one-tailed test, right? So we need to take that and divide by 2. So what did we get here? Two-tailed, let me write it down. For our two-tailed test, we got 0.0100. What if I had done this? What if I had just entered the same thing, but made it positive? Same exact answer. When you get a positive or a negative, it doesn't matter. It's going to give you the same. Whether you have the little piece over here, a little piece over there, it's the same amount. So your p is going to be the same, right? So don't get too hung up on that. But that's the problem, though. You need to figure out sometimes, well, am I talking about a negative or a positive? And you want to think about if you're talking about less than or greater than, right? Anyways, let's go back to this and take our two-tailed value that they gave us and divide it by 2. 0.005. And you know, when you use calculation, they're not really exact. They're a nice estimation, but I got 0.0050. The answer that the computer got was 0.0051. 1/10,000th is such a small difference that I'm sure that would fine. What about the critical values? The critical values are those places, wherever they happen to be, let's say they're here and here, I don't know, that separate the usual. Well, there wouldn't be one over here because we're just talking about one tail, right? We're talking about the usual values all the way over here, and then those unusual values over here. Ours, who knows? I don't know if that's here or if it's there or whatever, but this is the critical value is a different thing. It's asking what is that separation point. Our particular test statistic, the one that we're looking at, is could be the left or the right of that, but considering that we have such a small this, I think it's low, so the null is going to go. So I think the critical value is over here, and we're well into that unusual thing. But anyway, I need a the critical value. Okay, that's what we're looking for next. We have 24 degrees of freedom. So I'm going to here on the 24. And we were talking about a 0.05 significance level in one tail. So up here, area in one tail, 0.05, come on down, and we get 0.1711, I don't know, 1711, is that what that looks like to you? 1.711. Okay, does 1.711 make sense for where we're at on this? No. Look where we are. Here's 0 right there. We're definitely to the left of that. So even though on our chart we got 1.711, in our heads we should know, wait, our critical value has got to be over there to the left. So it's going to be negative 1.711. Okay. Critical value is a cutoff point between usual and unusual. Our test statistic, or our T in this case, is that one particular point where we are. That doesn't really mean we just then don't know if we're to the left or right. Excuse me, right. Anyway, 0.0050 is less than 0.05. That is low. That means that the null must go. Sad, but it must go. Which means happy. That kind of looked mediocre, but it should That was really bad. You can't tell. Anyway, sad and then happy over here. Okay, so we are going to reject it. So forget about these two that fail. And since we reject this one, then we are saying there is evidence to support that one. There is insufficient, there is sufficient. Sufficient. All right. What do the results suggest, if anything, about the effectiveness of the filters? See our sample? It was less than that. So it sounds like those filters are doing a pretty good job, right? Because we wanted it to be lower for taking tar out of there, right? That's what I think. Let's see what the choices are here. Yep, the results are inconclusive. Not really. They told us, hey, we're doing a pretty good job. Our average was low, and that low average seemed like a good thing. The results suggest that the filters are effective. I mean, we said that we think that it's going to be equal to 21.1, and we just proved that if it was equal to 21.1, it would be really, really unlikely for us to get a sample that had an average of 19.2. Therefore, it's lower than 21.1, which is good because we want the tar to be gone, so that makes those effective. Okay. 17, 18. Okay. There's only 12 on this homework, but it goes on and on, right? Maybe I should take one of these off. Maybe I will. If it seems like we're doing the same thing over and over. Rounded 3 places. Maybe we'll stop at 10. Let's see. I don't like that one. What about, was there 12? What was 11? 11 looked like. Yep, we'll stop at 10. Well, I'll go in and delete 11 and 12. Yay! Okay. For the following claim, find the null and alternative, test statistic, p-value, critical value, draw a conclusion, blah, 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 blah. If I was going to put this on the final, and I will, I'll put one of them on the final, not 4 or 5 of them, because it takes some time, but you want to make sure you have that ready to be going on that. Okay, choose the correct null hypothesis. What was the significance? The claim that the mean IQ score of statistics professors is greater than 133. How nice when they do that, right? They claim that it was greater than, that's our alternative hypothesis, and as always, we have equal to for our null hypothesis, so there we go. Sweet. Do you remember the formula for the test statistic? Maybe you do, and maybe you don't. I do. So we're going to be good for that. I have x bar minus mu over s over the square root of n. So x bar is 138 minus mu, which is 133. Standard deviation is 13. And the square root of n being 25. Brilliant statistic professors that they went out and found. Okay, so we have 138 minus 133, and then we're going to divide by this fraction, 13 over second function square root of 5, but I put that in there. Ooh. Why did it give me that? Well, I entered all stuff with no decimals in it. If you have that happen on your calculator, you know, I probably told you this before, but all you have to do is this, 138 minus 133. I could change that into a decimal right now, but let me just show you how you get this to happen anyway. And then you hit enter, you divide by this fraction, and then you realize, ooh, I haven't put any decimals in here. Stick a decimal in there somewhere, and then it tells it that you want a decimal answer. Okay, so I got 1.923. On the other hand, if I got the answer, I don't remember what the answer was before. What was it? 25/13, and I wanted to know, this was my answer, 25/13. No, I wanted to know, well, crud, I wanted that as a decimal. I don't want that up there. Get rid of that. Then I can just do this. Second function. Oh, heavens, forget it. You see that second function, fraction to decimal? Once you get an answer, you can change it to a decimal if you want that way. Sidetracked into oblivion. Find the p-value. Here they only want us to give the range, so you could definitely use your t-table for that, or you could go use your calculator and do that. Let's show you one more time. People are better with the calculator than they are the table. So you agree that our degrees of freedom is 24, and we're talking about 0.5, and we're talking about in one tail. So 24. Oh wait, we're not trying to find critical value. We're trying to find p-value. Yep, okay. So we know our t is 1.923. Yeah, so we're, sorry, I was leading you down the critical value, which is the next piece. Okay, so 24 is our degrees of freedom, and our t was 1.923. 1.923 is in between these two numbers. And so I just zip up, I'm talking about one tail, so I just zip up to one tail, and I'm in here between 0.025 and 0.025 and 0.05. 0.025 and 0.05. This is number 9. Okay, I believe that I'm truly answering that, but I don't know what happened to it. 8 continue. Anyways, oh, it's on here, that's right. Are we right? A, yes. Okay. Sometimes I try to check the answers before I tell you so that I don't steer you wrong. What's the critical values? Well, now I'm doing something different. I'm going to the 24, and I'm going to one tail 0.05 because that's my significance level, and I'm going to boom here to get that 24 and 0.05, and I get 1.711 again, just like I did last time. I guess I was just checking to see that I get the same thing again. 1.711 is what they gave me, but should it be negative or should it be positive? Well, where's my critical value? My test statistic was over here. Here at 1.923, right? And I'm talking about greater than, so I'm looking to the right. So yeah, that should be around here. 1.711 would be positive. So yeah, positive. And just 1 because it's not two-tailed. Well, I'm looking at this. See how my p-value, I don't know it exactly, but I know it's less than 0.05 or greater than 0.025. But that's supposed to be compared with 0.05. And I'm definitely less than that. So it tells me that my p-value is less than. Since my p-value is less than 0.05, then if it's low, the null must go. And if the null goes, sadly it's going, but happily we can support, there's evidence to support. So we're going to reject the null hypothesis and support the claim, yes. Yay! One more, and then we're done with all the homework for this quarter, and I'm a little sorry to see it go, but I'm going to find ways to keep myself entertained without it. Okay, this one is the one I have chosen in the past to put on the final, so maybe I will. Not this one particular, but this kind of thing where you're not given the information, you got to go in your calculator and get it, or you can use StatCrunch to get it, which I'll show you how in case you've forgotten. Anyway, assume a simple random sample has been selected and la la la. Listed below are brain volumes in cubic centimeters of unrelated subjects used in a study. Use a 0.05 significance level to test the claim that the population of brain volumes has a mean equal to 1100.3 cubic centimeters. They're saying that it's equal to. Therefore, we have to do, it could be less than, or it could be greater than, or in other words, not equal to. So we think that it's B. Yabba dabba da. Yes, we do. Okay, now the second thing is we need to do the test statistics, which requires that we have this, It requires that we need that, and we have this. So we have to go get those things. I'm going to take you really quick over to number 10 and show you one here. I know that your interest is fading. That's what we could use if we needed it later. But right here, I can do this, open this in StatCrunch. It throws that data in there. So sweet. Then you go to Stat Calculator. Z-Stats. No, what the heck? Summary Stats, sorry. Columns. Summary Stats columns. I use the 36X Pro, the Inspire, and the 84, and StatCrunch. And sometimes it's a little confusing about what I want. Anyway, you click on variable 1 so that it jumps over there because that's where your column is. You've got this column called variable 1. That's the one you're looking at. And then you just hit compute. And it gives you the mean, which is 1130.3. And it gives you the standard deviation, which is 117.7. Well, I'll say 713. I don't know. And then we know what we need. Okay, so that's how you could do that. Oh, I can't use that for my problem though. I don't have the same data. So if you're like me and you're working offline, which you shouldn't be when you're at the testing center, but you can enter this data yourself and get the values that way. I think I'm not going to do it. I just don't feel the need to show you this again. Once you have your two values, you plug that in, you get your t value. You get your t value, then you go find your p value. You can use the little thing on the computer. I will make sure and enter that as an instructor tip on your final, and will be on your midterm, on your final. And so you can use it there, or you can use your calculator. Bring whatever calculator you think you can bring. And then once we find our p-value, you compare that to our 0.05 level, and then you say whether we failed to reject or reject. If you're interested, if you want to do this problem for practice, you can see what those values are up there that you would enter into your calculator. The t is 0.811 and the p-value is 0.4383. That's quite a high p-value. And so obviously it's really high, and we think the null will fly. So we would fail to reject. And if we fail to reject, then that means the null is happy because we failed to reject it, which means, alternative is going to be sad, which means there is not sufficient or insufficient evidence for this based on that. Okay, so you can try that one. We've done several in a row, so I think probably don't need to bore you with more of that. Let's end this video, put you out of your misery. I have not put together a video for the final exam. I don't know. Maybe I will, but it would just be me doing the same problems over that you could go and look at the videos to get. So I think I'm not going to do those. But I do have let's take a look at what I have for you here in the world of this. You're coming down to it. Your final is a big portion of your grade. You've already done the midterm. You have some idea. When you look at your homework and tests, you're going to see that there's a practice final, and the final exam you cannot do 4 times. I have to change that. I will change it as soon as we're done talking. But the practice final, you get 1 shot. You get 4 shots at it. The final, you just get 1. So let's just hover over that so it blocks it out. And so I made it like the test, which has a 180-minute limit. You don't get extra credit for doing the practice final like you have in some of my previous courses. It's just there if you want to see it. The practice final is like the final with different numbers. And the reason I put the time limit and made it a test so that you could take it, and if you run out of time and you know that you need to spend less time, and you also then can go make better notes and have it arranged. Because for my test, you get to bring 4 pieces of paper front and back, whatever you want it to be, handwritten, printed out, I don't care. 4 pieces of paper of notes. You can bring the book if you buy a book. A lot of people won't have a book, and I'll tell you that books aren't that useful really. I mean, there it is, I guess, if you haven't done things and you think you might, but more useful would be your 4 pages of notes. What would I do with those 4 pages of notes? I would go through and work the problems out for the practice final. And at first, when I did it, I wouldn't worry about fitting it onto 4 pages. I would just work out the practice final. Maybe it takes you 10 pages. Then you see the ones that you missed, you go back and fix those, and then you take it again, and you say, okay, I'm going to limit myself to 6 pages or whatever. It's less than what you did the first time. You go through and take it, see which ones you missed, fix those. And then at that point, maybe 2 times, you're sick of it. You're not going to do it again. Then you go back and take your second best, or whichever one, your first one was best, your second one was best, whichever one was the best, and you're going to condense that down into 4 pages, which is 8 sides. You should be able to get everything on there if you've written it out nicely. And do it in the order that it's showing. I don't remember if it's the exact same number of questions, but there's nothing on the final exam that didn't show up in the practice final. It could be that your practice final is 40 questions and your final is 30. It might be shorter, but everything will be in there. So that's the best way to prepare for that. No extra credit for doing the practice final, but it's a gift to you for me to say this is what to expect. And you get to do it 4 times. Final you get to do 1 time, all right? Have a great day. I'll see you next time. My computer's got bad messages coming up, so I'm going to go. Have a great